Our guest speaker is John Brinkmann. He's a retired affiliate professor at New Mexico State University. He was part of the Sloan Digital Sky Survey, one of the most ambitious and influential surveys of the skies in the history of astronomy. He helped build the instruments used for the survey at Apache Point Observatory near Sunspot. He was a scientific instruments engineer, manager, and systems administrator. Just so you know a little bit more about the Sloan Digital Sky Survey, or SDSS, since the year 2000, the SDSS has obtained deep, multicolored images covering more than a quarter of the entire sky. So they're just building a repository of images, and it's pretty fascinating. So John's going to discuss the evolution of our understanding of black holes since the very beginning, when in 1676, when, I don't know how to say his name, Ole Rømer, maybe it's something like that, demonstrated that light has a finite speed and find that light could not escape from a sufficiently large object. He will explain the That's why we're all here, so we can learn.
Hi, guys.
So I'm going to give the stage to John, and thank you for coming and enjoy the lecture.
Good morning. Can everyone hear me? Even way in the back there? Okay. I'm John Brinkmann. I was at Apache Point Observatory for almost a quarter of a century. We're doing the Sloan Digital Sky Survey. And in my retirement, I decided to come and volunteer here, which I would encourage anybody who's interested in space or in rocketry or any of the affiliated sciences to come and volunteer as well. I work as a docent up in the museum, as well as in the last couple of years I've been helping with the archives. As Olga said, my talk is about black holes, and it's about trying to conceive, and humanity's attempts over the centuries to conceive of what in the world they were talking about. How the theories have advanced, how various people have come up with different ideas. And so I'll do that. That's the first part of the talk. And then the second part, I'm going to talk about, or I have a video actually from a fellow from JPL who does scientific visualization for Caltech and for JPL. So when they have a press release or something like that, and they want a fancy graphic video to go with it, they go to him and he puts something together using software packages that is normally used to build special effects for movies. And he gave a talk a year ago. I went back for the American Astronomical Society meeting in Madison, Wisconsin, where I got my PhD. Sort of as a mini reunion, as well as to reacquaint myself with my friends and so forth in the society. And he gave a public lecture. He gave a talk about several different projects he had worked on. One of them was working on the black hole simulations for the movie Interstellar, which many of you may have seen. And that movie actually hired a well-known black hole theorist by the name of Kip Thorne from Caltech. And Kip came to this fellow and said, you know, I want to take and get the visualization right. And so they worked together to get it right. And so he talks about how they do it wrong as well as how they do it right. Anyhow, moving on from that, I will not be talking about any of the various theories, many of them obviously wrong. If you look at what we developed over the centuries, because there are just so many of them. We'd be here for the next month or so every day talking about them. So I'm not going to talk about that. And with that in mind, I've got a little cartoon that I'd like to show you if Paul would get out of the introductory video up there. Paul's running the computer for me. There we go. I'm a big fan of Calvin and Hobbes. It was a cartoon couple decades ago. Bill Waterston did it. And he has a cartoon about the theory of relativity, which is what black holes are all about these days. I'll give you a moment to read that and find out one of the harebrained theories about black holes or about relativity that Calvin's dad is feeding him. I hope you appreciate his humor. Alrighty, can we move on to the next tab, Paul? So I put together an interactive here instead of a normal PowerPoint, just because there is so much to talk about in the history of black holes, and it actually goes back before 1784 quite a ways, because in the early days, if you probably remember your history of astronomy a little bit, you know, in ancient times, people sat around the campfire and looked up at the sky and wondered what it was, and everybody figured it was a big dome over the earth with little holes that let light from fires on the top of the dome through or whatever. And our understanding progressed through folks like Ptolemy and Copernicus. Copernicus says, and then well, before that they came up with the theory that the sun was not the center of everything, the earth was, and everything moved around the earth. And there wasn't even any concept of gravity. Everybody just figured everything was like it is on the earth, right? And so whatever we feel on the earth was whatever there was out there in the planets and the stars. Shortly after that, Copernicus came along, and by looking at Kepler's data and various observations of Ptolemy, he realized that no, it works a lot better if you put the sun at the center and let all the planets rotate around that. And we have up on the 5th floor a armillary sphere, which was an early attempt at a planetarium type of thing in a 3D globe kind of an arrangement. The one that we have doesn't work. It's meant as a garden ornament, but it's the same basic concept. And with that, then Kepler came along, and he took the observations and put it together, and he came up with these empirical laws for how the planets move in ellipses and so forth. All right, and this is where Ismail Bilal, I don't know how to pronounce that, I'm not French, looked at that and he said, well, clearly there's some kind of an influence that the sun has. If you click on that, it says, as for the power which the sun seizes or holds the planets, it becomes weaker and attenuated at greater distance or interval, and the ratio of its decrease in strength is the same as in the case of light, namely the duplicate proportion, but inversely of the distances, that is 1 over d squared. He was very verbose about it. But he realized that there is that gravity is not the same everywhere, here and there and so forth. But people were scratching their heads, they didn't know what to make of that. And it took another 30 years before Ole Rømer, who came along in 1676, he was, if you'll click on Ole there's a picture of Ole. He was a Danish astronomer, and he had been working on a suggestion by Galileo. If you may have recalled, there was a big problem with ship's navigation back in that era, in the 17th century. And I believe it was the King of England established a reward for anybody that could figure out how to figure out the position of the ship to within a mile or two. Because they could do latitude using the sextants of the time, but longitude was difficult because the Earth rotated and the sky rotated, or didn't rotate, or appeared to rotate around it. And so you had to have a precision measurement of the time. And so one group of people were clockmakers and were trying to make a precision clock that you could take on board a ship, and it could be bounced around with the waves and still keep proper time. Galileo took a separate approach. He said, well, we've got a clock out there in the universe. And Galileo had been studying, as you recall, Jupiter. He had built one of the first known telescopes that was used to look at the sky, and found out that Jupiter had 4 moons at the time. That's all they could see. And so he said those moons move in precise orbits, and so we can use those as timekeepers. If we can track, the number of orbits, we can tell what time it is to within a minute or two, which was good enough for the king. But Galileo didn't get to do that. Well, Ole was experimenting with that method, and he was in Uraniborg, which was where Tycho Brahe had established an observatory in Denmark, and he had a friend in Paris, and they were both observing the moon Io, which today is known to be a very interesting moon, but that's another topic. And they had determined quite accurately the distance between Paris and Uraniborg in that way. And so, but they were noticing in their data and some of the data before them that the timings varied, and so they are having to average out these times. There were minutes of time difference between the time it took for Io to make an orbit, and they said that's not right. So he went to Paris, talked to the guy, and the guy came back to Uraniborg, and they spent about a dozen years getting data on the moon Io. And he says, well, the only way that I can explain this minutes of time difference is if light doesn't travel instantly from here to Jupiter. And if the Earth is moving in an orbit, that means that the time delay for going to Jupiter and back differs every time we make a measurement, because the Earth is in a different position. And Jupiter is moving slow enough we can pretty much ignore that. So he put that together, and he said it took about 11 minutes after he did that. It would take about 11 minutes for light to get to the sun and back. And the distance to the sun was known. It had been known since ancient times. I think it was Eratosthenes or someone like that had measured the length of shadows at pretty much the same time in 2 different spots in the Middle East, and was able to determine the difference in angle. That triangle told them how far it was to the sun if they knew how far apart the 2 sticks were that were projecting shadows. And so that number gave him a speed of about 220,000 kilometers per second. And that's pretty close to our accepted value of 300,000 kilometers per second now, which you have much more accurate ways of doing that. And so he realized that the light moved in a slower fashion than instantaneously. And the next guy to come along was Isaac Newton, which we got here. There's Isaac. And he had, of course, he took the laws of Kepler and applied his mathematical skills and came up with the Newton's law of gravitation, which agreed with Ismail back there that it was a 1 over distance squared type of relationship. And that allowed him to do that. But in addition, he came up with what he called a corpuscular theory of light, that light is little bitty particles of matter, like little bitty fireballs that are flying around. And based upon that, again, about a century later, Jean Michel said, well, if it's a little bits of matter flying around, we know that by this time they had artillery and so forth, that matter gets attracted to a body in the sky. And he said, well, there must be a possibility of having a body big enough in the heavens who has gravity strong enough, based upon Newton's gravitational equation, that these little corpuscles can't escape. So they'll go up so far, and then they'll come back down and strike the surface of the body. And so he figured it out as about 500 times the mass of the sun in his calculations. And he said, well, if we have one of these out in space, the light will never reach us. It'll go up, it'll come back down, it'll go up, it'll come back down. but we'll never see it. And so he called these things dark stars. And that name, dark stars, held until the 20th century, when the press adopted the more popular term called black holes. But that didn't mean you couldn't see it. If you got close enough to it, you could see this light coming up and looping back down, and you would, you get within however close you needed to be, and you could suddenly start seeing light from these dark stars. Alrighty. So he wrote about that and presented a paper, and then another decade later, Laplace, who was a famous mathematician, you may have heard of him if you were taking any undergraduate junior or senior level of mathematics. You learn about the Laplace transformation that's used extensively in electrical engineering. Laplace said, yeah, that was very interesting, and he also used the idea that light was corpuscles, very small particles, including newtons. So by this time we had dark stars out there, but nobody knew what to make of them. They couldn't see them, so it was sort of immaterial what they were. But the theories were interesting, and all these guys were theorists. Anyhow, Newton, when he had given his theory of gravity, said that there's a constant that relates the force that you feel to the mass of the bodies that are involved. And so he he was a good friend. Henry Cavendish was a good friend. Notice they lived about the same time. Cavendish was about 7 years younger than Michel. Well, Michel had built an apparatus to allow them to measure that constant in the laboratory by using lead balls. But he passed away before he had a chance to run the experiment. And so Cavendish took the experiment and set it up, and he had to make a few adjustments to the apparatus, but he was able to use it in order to get it to work. So if you'll keep scrolling down. And he gave Michel so if you'll click on that very bottom thing, this is Cavendish's torsion bar experiment. No, the next one down. No, that didn't work. Oh well. Well, I thought that would work, but it didn't. But basically he had a rod about a yard long and had two 1-pound lead weights on either end of it, so it balanced. And in the middle, he tied it to a thin thread that was attached to the ceiling or support above it. And then he had two big lead balls that were about 10 times the little balls, and he moved them close on opposite sides of that rod. And as they got closer, the rod would turn as the balls attracted to each other. And he could put a mirror on the rod and watch a light beam move across the wall in the distance, and he could measure the angular distance that torsion would move it, and he could calculate the constant of gravitation. He came within about 10% of the value that we use today, that's used for calculating orbits of rockets and satellites and all kinds of things. There you go, there's an animation. And you click play down there, yeah, there you go. So there's the big balls, and the light beam bends. So then he had a pretty good idea, at least under Newtonian gravity, what was going on. And then along came another mathematician, William Kingdon Clifford, who was his work is still used today. He was very interested in nonlinear geometries, which were very popular in the 19th century. And he did work on what they call Clifford algebras that allow them to mathematically describe a geometry that wasn't a nice regular grid, which we call Euclidean geometry, which you learn about in trigonometry and so forth, if you can think back to your trig classes or geometry classes. But he suggested at the time, this is in 1876, that that gravity might not be like light, little corpuscles of things that were pulling things together, but it was actually a nonlinear geometry, like so that space itself was not linear. And Einstein, of course, had studied that in school and adopted that as in the back of his head to use 40 years later when he's working on, or more than almost 40 years later when he's working on his general theory of relativity. And there's Einstein. But before that, in 1905, Einstein presented his first theory of relativity. And this one is what's used for objects in motion, uniform motion, moving at a constant speed or velocity, and allowed people to determine how the properties of objects at that speed were traveling. And it's called the special theory of relativity. His wife, Mileva, was also a physicist. They had met in undergraduate school. She was 4 years older than he was. And they fell in love, ended up getting married. And there's a big controversy. In fact, there's a book called Einstein's Wife about how big her contribution was to his work. They were careful because she was a woman and she would never be accepted as an author on a publication or even accepted as a professor at the college. But so they were very careful to keep her name out of everything. But their son, Edward, recounted that he would see his mom and dad sitting at the kitchen table for hours and hours talking about physics, which of course was way over his head. But he was amazed at how closely they worked together. So a lot of people think that she should deserve some credit for the special theory of relativity, at least. Einstein was a rather big philanderer, and by the time of the general theory of relativity, which comes along as down here at the bottom in 1815, he was having an affair with his cousin, who he eventually married. They didn't have any more kids. Einstein just had the 2 kids that he had with Mileva. And when she found out about the affair, she left him, and a few years later they were divorced. And her influence over him was gone. So anyhow, in the meantime, Einstein had another school chum, Marcel Grossman, who he was talking with about stuff. And after Einstein had done this theory with objects in uniform motion, called the special theory, he wanted to extend that to accelerating objects. And so they were looking for a way to incorporate this idea of space-time into that, that we had heard about from Clifford. But he didn't have the math skills for it. If you recall the famous quote by Einstein, it says, I'm sympathetic if you're struggling with mathematics because I had a lot of trouble with it as well, even though he was a fairly good mathematician. So somehow, I don't know whether it was Grossman or someone else suggested that he contact a famous mathematician. Well, there was a fellow by the name of Hilbert that was a very famous mathematician, and so they went to him, and he helped them out with it. But in the meantime, Hans Reitzner, who was the first to solve this problem of using a new kind of mathematics to understand gravity, and he made really the first solution to that, and it's called the Reitzner-Nordström metric. And basically what you need is math. Most math describes, I throw a ball into the air and it comes down. So you're looking at the ball as a point mass that goes up and down. But Einstein needed something to describe something that was operating over a whole volume of space. And that required this new mathematics that they call tensor calculus and algebra. And that's what Hilbert brought to the table at that point. So they worked on that, he and Grossman and Hilbert, for several years to develop the theory. Einstein was preparing to present his results in a Prussian Academy in November. Well, a week before, Hilbert had completed all the work which he had given to Einstein, but he went ahead and gave lectures a week earlier and presented the work. So, as you can tell, Einstein was very good about drawing upon other ideas. He was an idea man, and he could pull together the mathematics to create a concrete physical theory from disparate mathematical ideas. Well, Einstein presented his results at the Prussian Academy. Well, some of the people in the audience obviously were taking notes, and they had a friend who was serving in the Eastern Front in World War I, in Poland, I believe it was, as a artillery officer calculating where to point your cannons to hit a particular target at a distance away. And in his spare time, he was having a great time following what was going on in physics. And they sent him their notes from Einstein, and Carl Schwarzschild is his name, solved Einstein's equations for a point mass. And he came up with the case that at a certain mass, indeed, light, which by this time was known to be not a particle, but it was made of photons, which were not really particles and not really waves. They were something called quanta, but it had a definite speed, and light could not escape from that. And so the critical radius, which you can't escape from a black hole, is known as the Schwarzschild radius in that case, and it's dependent only upon the mass of the black hole. Anyhow, so a lot of people were intrigued by this new mathematics used to describe the way the universe worked. A fellow by the name of Paul Ehrenfest, this little fellow here, was working with mathematics of higher dimensions, 4 dimensions, 5, 6, whatever. And he realized he was trying to solve the equations in higher dimensions, that you don't get stable orbits for anything but a 3-dimensional space like what we live in. Any higher dimensions, any slight deviation in the orbit, another rock going by a satellite or something like that would perturb it enough to cause it to either fly off into space or to crash into the object that it was orbiting, whether it was a star or planet or whatever. And so that pretty much rules out, if you hear some theories about gravity leaking into higher dimensions, like there's been recently publicized about the string theory that uses 11 dimensions, can't be right, because we wouldn't be here. We'd have fallen into the sun or gone out into deep space and froze to death eons ago. So Ehrenfest did some very important work that's valid even today for the theories that you're about. And then, in addition, after Hilbert and Einstein published their work, and they weren't finished, they were still working on it, because Einstein had realized that he couldn't come up with conservation of energy under his new theory. Energy was not conserved, and he was tearing his hair out trying to figure out why it was not conserved, because obviously he could do laboratory experiments on the Earth, and energy and momentum were both conserved. And Hilbert was working on it, Einstein was working on it furiously. Einstein came up with an equation and sent it to Hilbert, and Hilbert had brought another woman on board, Emmy Noether, spelled it like note or not no ether, when I first saw the name, I thought, no ether. Well, that's part of what Einstein discovered, that there was no ether. No, that's her actual name. But she was a brilliant mathematician. Einstein and others said she was the most important woman in the history of mathematics, going back, thousands of years. And she liked to work on the mathematics of symmetry. And most people know what a symmetry is. It's something about which you can move an axis or a point about which you can move something, and it doesn't change how the object looks. So if you take a ball, you can rotate it any way you want and it still looks like a ball. Or if you take an object and you move it left, right, up, and down, the object doesn't change. So those are both symmetries. And so she proved mathematically that all these conservation laws are based on a symmetry. Conservation of momentum is based upon the fact that you can move an object and it stays the same no matter where you move it to. Conservation of energy is similarly based upon, depending on which theory, whether you use the Newtonian or Einstein, a different symmetry. Well, it turns out that if there is nothing in space, so space is a uniform grid, then you have these symmetries. But when you start putting matter into space, things are no longer symmetric under general relativity. So it's made perfect sense that nothing is conserved in general relativity. Well, that put Einstein's mind at ease. They stopped trying to make it work. They realized that you could do it locally in a small patch of area like where we are here, and you could get a symmetry because space is relatively uniform where we're at. But if you do it on a cosmic scale, there is no symmetry. If you want to learn more about Emily, there's a very good video on YouTube. There's a YouTube channel called Veritasium. And all you have to do is go on YouTube and Google her name, or search for her name, and you'll find the video. It's about a half hour, 40-minute video, but if you're interested, it's very good. Anyhow, she did not get a professorship. She was working with Hilbert for years and years, but the best she could do is get a lectureship. But she loved to teach, and so she was happy doing that. But they would not promote her to a full professor, even though she'd done this seminal work that was far beyond what most of the other physicists and mathematicians had done. But she had a Jewish heritage, Jewish blood, and when the Nazis came to power in the early 1930s, they kicked her out even from her lectureship. So she got an offer to come to Bryn Mawr in the United States in the early 1930s, where she went and was given a professorship and taught until her death a decade or two later. But she's recently come to light. There's a couple of biographies. There's a scientific biography or a mathematical biography, as well as a general biography about her out there that you could read if you're interested. I haven't read them, but I suspect they're quite good. Anyhow, at about the same time, 1918 and the early 1920s, there was a big flurry of activity, people taking these new equations that Einstein had promoted in general relativity and solving it for different types of black holes. For black holes that had charge, black holes that didn't require even Einstein's equations to generate them. And finally, black holes that were in various uniquely spherical symmetric situations. As long as it was spherically symmetric, it didn't matter what was inside, you got the same result. Until 1931, when a Indian mathematician and physicist, Chandra he's going by, because I'm not going to try and pronounce that. He goes by, won a competition to come to England and study in England. And so he won that competition and went to England at Cambridge to work with Ralph Fowler to work on his PhD. And so he decided to start looking at the practical aspects of this singularity that Schwarzschild had developed a couple decades before. And they had, and he did the calculation to see what would be needed for that to occur. And so he worked it out, and he said, well, it won't, any matter at all won't collapse into a dark star. It takes a certain amount, and he pulled in quantum mechanics and showed that stars of fairly low mass will not form a black hole. They form a very compact object called a white dwarf star, which doesn't rely upon the same energy source, but it uses the degeneracy of the electrons. A white dwarf relies upon the pressure of the atoms are so tightly pushed together that the electrons are pushing against each other because they're all the same charge, and it holds the star up against the force of gravity. And that was the first time that anyone had done that. Well, people scratched their heads a little more about that, and 8 years later, Oppenheimer, who is the same Oppenheimer that we talk about when we talk about the Trinity test and the Manhattan Project, he was in California, and he and another fellow decided to take a look at that and see what happened if you started using nuclear pressures instead of electron pressures. And they came up with a mass limit for what's now called a neutron star. It would go continued attraction, separate, and then he said, and they also went to the point and said, well, if that's not enough, then it will just collapse. We don't have anything in the nucleus that'll prevent the collapse. And so they were the first persons to calculate a limit for the size for a black hole. But they said that the sun should be a black hole in 1939 with another fellow, George Volkoff. They calculated upper mass limit of a cold non-rotating neutron star to be approximately 0.7 solar masses. So we should be orbiting a black hole if he was right. So they knew that wasn't right, but they published it anyway. Another guy came along after the war. There was a hiatus, everybody was off working on the Manhattan Project or something like that. A guy by the name of David Finkelstein said that, well, this Schwarzschild radius, this event horizon, is a region where nothing can escape. They hadn't confirmed in all these years since 1916 to 1958 that that's actually what was happening. So as you can see, progress was slow. People were having to assimilate all these inconceivable ideas before they were happy with what was coming along. But then in the 1960s, progress started to pick up, and it's continuing to this day. Roy Kerr, the next fellow, was interested because no one had been able to solve these equations for a rotating object. And just about every object that we see in the universe rotates in some degree. The Earth rotates, the Moon rotates once a month, or once in orbit, and almost every star that we observe has got rotation to it. So black holes are all going to have a rotation to them. In fact, they rotate very fast, and it's the same conservation of angular momentum that you have with an ice skater. When they go into a tight spin and they pull themselves together, that speeds up the rotation speed. So black holes were thought to spin very fast instead of a matter of days or weeks. In the case of a star, they spin in a matter of seconds. But to this point, no one had all this was all theoretical. And people were, like I say, scratching their heads and thinking about these for years. Finally, in 1963, about the same time Roy Kerr came along, observational astronomer Martin Schmidt at Caltech was using polymer 200 inch to look at a very strange object which no one could explain. Half the community thought it was a nearby star, but all the evidence was showing that it was billions of light years away, and nobody could imagine anything that would generate the energy needed to make it glow as brightly as it did, billions of light years away. But he used the 200-inch telescope to take data on it and proved that it was indeed 3 billion light years away, and that it was shining brighter than all the stars in our galaxy. And so they were, the next year, a fellow in Russia, Zeldovich, proposed that all that energy could be generated if a black hole was eating up other objects and forming a disk, ripping the objects apart to form a disk of gas and rubble and so forth that was falling into the black hole and releasing all this energy. So they had a theory of what was going on, and they could calculate that huge amounts of energy were being radiated by these things. And so it fit the observation. Well, the next year, a fellow at NASA, Hongyi Chu at Goddard, came up with the word quasar for quasi-stellar radio source, because they didn't know what it would look like. It would be some kind of a massive star or what it was, but he called it a quasar, and that's stuck to this day. And so the next year, a journalist, Ann Ewing, actually used the term black hole in writing. Nobody knows where she came up with the name black hole, but it was in print at least, and to describe these compact objects that were eating up everything around them. Then Sir Roger Penrose, who ended up being a good friend of Stephen Hawking, by the way, went ahead and he was using yet another form of mathematics called topology to describe these things, and was coming up with some interesting ideas. And so he proves that an imploding star will necessarily produce a singularity once it's formed on an event horizon. In other words, once it's collapsing, once it crosses that point of no return, it has to keep collapsing. It can't come back out. So the other thing that a black hole can have, it can have an electric charge. The sun is probably charged because it's shooting out electrons all the time. And so this next fellow, Ezra Newman, well, that's Penrose, he solved the equation by throwing the charge into the mix for the stars that were creating black holes. So now we've got stars that aren't rotating and are just collapsing. We have stars that do rotate, and we have stars that have electric charge. And that pretty much completed the gamut of the characteristics of stars that they could think of at that point. So by 1965, they had a pretty good idea of what's going on. Zeldovich came back and said, well, you know, you can look for black holes since you can't see them, but if they're in a binary star system, they're probably gobbling up their other star, their sister or brother star, and generating these jets and accretion disks. So you might be able to see them. One will be bright, and the other one will be dark, but be X-ray bright, because that accretion disk would be pouring out all kinds of X-rays. Well, nobody had found anything quite like that at the time. So another woman, Jocelyn Bell, was a graduate student using the telescope at John Roll Bank in England, was looking for radio sources in the sky. And so she would run, and they didn't have digital equipment back then. Everything went onto a chart recorder, which would was a roll of paper, kind of like a toilet paper roll, that they had a pen that would record the signal as little squiggles on the paper. You've probably seen it in the movies with a lie detector, the little squiggles. And so she was running these experiments, and you just let them run all night, and she'd come back later to look at them. Well, one night she's going through the data, and it took her 3 months to find this squiggle that she couldn't identify. That was a repetitive pulse. And at first they thought, well, it's an alien civilization that's broadcasting to the universe every second or so, sending out a pulse. So they called it the little green man, or thing, called LGM-1. Well, somebody said, well, if they got a rotating black hole or a neutron star, it can act like a lighthouse and be shooting out a narrow beam that's rotating very fast, and we just see it when it flashes by it, just like you see a lighthouse beacon when the beam goes by you. And so it was identified as a rapidly rotating neutron star. And since then they found many of these, and they've come in very handy for various studies that they've done. So the next thing is also something, if you're hearing about new black hole theories today, is Werner I. Israel in 1967 did a study, and he showed that there's only three things that you can see. You obviously can't see what's going inside that event horizon because nothing gets out. But when a black hole collapses, you can only measure three quantities. You can measure its mass, you can measure its charge, and you can measure its rotation. As it spins around, there you can see the accretion disk being pulled with that spin. So if you see people, like I just saw a paper a few weeks ago by string theorists that said, we know what's going on inside the event horizon. I'm going, yeah, right, you do. Because nobody's going to be able to verify that theory is correct, because you can't see inside there. If you can't relate it to one of those three quantities, there's no way anybody will ever be able to prove that theory. Anyhow, so the term black hole was not widely used at that point, other than by a few people in the press. Well, John Archibald Wheeler, who was a professor, was teaching a class, giving him the black hole theory, and one of the students asked a question and called these dark stars a black hole. Well, John was a guy that liked to take and have a little fun in his lectures, and so that term stuck, and a short while later he gave one of the plenary lectures at the American Association for the Advancement of Science, and used the term. Well, that kind of cemented it in the scientific community as well. Everybody was calling them black holes. The term dark star was put on the shelf. Anyhow, after that, in the latter 60s, there was more work. They had to figure out how do these particles in the accretion disk move, and so people were doing studies to measure trajectories of particles in the accretion disk. Roger Penrose comes back and proposes a process for the way that energy can be transferred from the spin of a black hole into the accretion disk, so that you can actually, by measuring the accretion disk, you can tell what's going on in the black hole. And then he calls it the cosmic censorship hypothesis, which is where the universe doesn't like black holes, which goes back to what Einstein, because Einstein didn't believe that dark stars or black holes or singularities exist. In the 1970s, thanks to NASA, put telescopes in space that could look at wavelengths of electromagnetic radiation that didn't penetrate the Earth's atmosphere, especially X-rays. And they identified the first stellar black hole called Cygnus X1 that was a binary, the one where the black hole was eating its companion star up and producing lots of X-rays. And then Stephen Hawking came into view. He was doing his postgraduate work, often with Roger Penrose, and showed that once a black hole forms, that it can't get smaller. The event horizon can't shrink along with the black hole in the middle of it. So that's a fixed entity. And there's a picture of Hawking, and I think it's 2010, I think it is. He was visiting Caltech, I believe. That was before his health deteriorated even further. So then the next fellow, James Bardeen, came along just shortly after Hawking and said, well, you know, you could take and look at black holes thermodynamically then, because Hawking had used some of the same arguments of entropy and the laws of thermodynamics when he said that the area can't decrease. And so he, along with Stephen, came up with a set of thermodynamic rules for black holes that they proposed. And there's still ongoing discussion now, 50 years later, about that. And so they have not been universally adopted, but they came up with 4 laws for that. But Bekenstein did additional work on that, and he showed that if you consider that black holes have an entropy, and entropy can't decrease under the second law of thermodynamics, then and that the area is proportional to the entropy, the area of the event horizon, then the event horizon can't decrease. So that agrees with thermodynamics. Stephen came back and came up with his most famous thing, that at the event horizon, that particles, including light, form in quantum field theory, that everything around us, this room that we're sitting in, is filled with what they call vacuum energy that the quantum theorists had come up with a few decades before that. And that energy, if it's powerful enough, can form pairs, a particle and an antiparticle. And they form for just an instant, and then they recombine and form the original photon that created them. But Hawking realized that in a strong gravitational field, one of the particles will be pulled away from the other one, and they can actually separate and not recombine. And and if it's at the event horizon, one of them will fall into a black hole, and the other one will leave. So that was determined that black holes could evaporate, that these falling in antiparticles will eventually annihilate the singularity at the center, and the black holes will get lighter and lighter and lighter until they don't have enough gravity to stay together, and then they'll blow up. Another fellow, James Bardeen, found out that the spin of a black hole acts like a gyroscope that stabilizes the accretion disk. So the accretion disk will rotate, but it won't move up and down or shift. Theoretically, without the presence of moons, an accretion disk like around Saturn, if Saturn didn't have any moons, the disk around Saturn is not stable. It could shift its tilt however it felt like, but the moons keep it locked in the orbit that the rings are in now. And I also create the gaps between the rings as well. And then they identified a microquasar, a binary black hole system that wasn't a massive galaxy spanning thing. Charles Townes actually observed, by looking at the gas at the galactic center, that it was moving at such high velocities, there was something very massive at the center of our galaxies, with a mass of several million solar masses, several million suns. And they couldn't see anything there. They didn't know what it was, but they weren't sure whether it was obscured by dust or whether it was a big ball of regular stars or what it was. But they knew that there was something very massive at the center of the galaxy in 1994. That was 30 years ago. And now we move on to this century. Astronomers at German Institute, Max Planck Institute for Extraterrestrial Physics, present evidence that 3 million solar mass object is indeed a supermassive black hole. And then the Chandra Observatory does the same thing. And various other observations occur that we're getting evidence that there is evidence to support that there are black holes at the middle of the galaxies. And finally, a gal by the name of Ole Rømer, who's an astrophysicist at the University of North Carolina, takes another look at the Hawking radiation. And she realizes that the Hawking radiation starts before the event horizon does. And so as the star is collapsing, the Hawking radiation prevents the star's collapse. And so it either stabilizes or blows the star apart before it can form a black hole. So she says, black holes are a myth, they don't exist. About the same time, Hawking reads her paper and agrees, and he says, I was wrong in a lot of ways because I didn't take my radiation calculations far enough in the formation of the black hole. I just took the black hole and figured out what was going on with it. So Laura, 10 years ago this month, in fact, organized a conference in Stockholm with Hawking and a bunch of other of these names that you've seen up there to discuss what happens in that case. We see these things out there. They look like black holes. They act like singularities, but the math says they can't be black holes. And that's pretty much the way the state of affairs has been the last 10 years. There have been all kinds of theories about what's going on, but no one has identified something that can be observed and proven. You'll see black holes called fuzzballs and all kinds of different topics. But now the LIGO collaboration has come along, and the Event Horizon Telescope, and they're getting us more data on black holes. But the bottom line is, we still don't know exactly what a black hole is, or even if it's black anymore, because Hawking radiation emits radiation that you can see, so the black hole isn't really black. Alrighty. And we got Greek. So can we go to the next tab, Paul? And so we're talking about space-time, so who better to talk about space-time than the doctor who travels in space and time?
Time is a strict progression of cause to effect, but actually, from a non-linear, non-subjective viewpoint, it's more like a big ball of wibbly-wobbly, timey-wimey stuff.
So this is, up until Laura came along here, this was our best idea of what a visualization of a black hole looks like. It has various components. It has the accretion disk, has the event horizon, the singularity, and the accretion disk spins around and it shoots particles that don't fall in out into a jet. But like was discovered several hundred years ago, light can form orbits just like material objects do around this. And so there's a photon sphere that's at about 1.5 times the radius of the singularity, where light is trapped in an orbit. And it's in a circular, most of it is in a circular orbit, because it turns out in the space-time that anything other than a circular orbit doesn't last very long. So there are elliptical and hyperbolic and parabolic orbits, just like we have for regular matter, but those don't last very long, or they get kicked out of the system or absorbed in the accretion disk. So there's this thin photon sphere. So I would ask you to remember that. This is from the Event Horizon Telescope, which is euphemistically named because they've yet to see the event horizon. They see the accretion disk, but none of these other components are in their images. I'm anxiously awaiting the latest work. They want to create a enhanced Event Horizon Telescope to do more than that. So next we'll go to, it's a short 5-minute video from JPL on how to visualize black holes.
Well, another thing that we visualize a lot is black holes, because until recently we couldn't even get a picture of them, and even now they're pretty low resolution. So historically, of course, people have loved black holes, and pop culture has embraced them through the years. But when you look at the way black holes show up in pop culture, I decided you could actually basically bin them into 3 main categories, right? On one side, you've got your bowling balls. Then you've got your bathtub drains. And then if you're J.J. Abrams, thinking he knows anything about Star Trek, they become flat, swirly things with lots of lens flares and things popping out of them all the time. So, and yet they're still black holes. So now, admittedly, we can't really blame pop culture because astronomy visualization has been pretty much the same over the years. I have done my fair share of bowling balls, I will admit. We've got the bathtub drains, and frankly, the fact that the bathtub drain looks a lot like space-time diagrams that we're always showing for black holes, and it's obviously a confusion of a 2-dimensional extrapolation of a 3-dimensional manifold into 4 dimensions. You lose all that context, it looks like a bathtub drain. So of course, that's the way the pictures get drawn. But we've known for over 100 years that black holes warp light, right? So why don't we see lensing when we show black holes? And I think there are kind of 3 big issues here. The first is which a lot of artists don't understand general relativity, which is not their profession. It's not their job. And when they are asked to do something that in a project that doesn't involve a scientist or doesn't give a scientist much influence over what they're doing, it's not their job to figure this out. We're supposed to tell them this, right? But even if they do know about it, gravitational lensing is a lot harder to create. And the reality is, cutting corners is necessary to meet your deadlines, whether it's for a motion picture, a TV show, or a press release that is going out on Tuesday, whether or not the artwork is done. So we have to sort of balance issues here. But the third and most insidious reason, I think, is that gravitational lensing was not expected in black hole art. Balls and drains are deeply aligned with entrenched misconceptions. And so there are people who say, well, just do it that way because it's less confusing. Now, that might sound embarrassing, but it's something I've run into again and again. Now, that said, I have made an effort over the years to try to get warps into the black hole image whenever possible. My colleague Tim Pyle, back in 2008, did an animation with Michelle Fowler called Spaceship Spitzer, where they visited a black hole. And I dug my heels in and said, look, you need to show lensing in this. This has to do this. And he came from a Hollywood background. It's like, no one knows what that is. That's going to confuse people. But I said, look, this is our chance to do something new that people don't get to see. Michelle was on board with it. So I think Tim was actually happy with it ultimately. But there's a lot of misconception you had to overcome on the argument that people won't understand it. But even when I've done science releases like this image from 2010, I got pushback from the JPL media office. Like, well, we did, yeah, we showed it around the office, but people didn't understand the little warpy thing. Can you take that out? And I was like, no. As anyone who's worked with me knows, I can get very, very stubborn. So we've got this stuff in, but what happened in 2014? Something changed. There was a little movie a decade ago called Interstellar. Maybe you've heard of it. What's special about this movie is that the director, Chris Nolan, actually wanted to tell a science fiction story in active collaboration with a scientist, Kip Thorne. And when it came to the visualization part of what they were working on, they brought in somebody who could speak the data viz language, AJ Christensen, right over here, to work with the visual effects team to help them incorporate relativistic ray tracing into their production code. And in the process, create visualizations of gravitational warping so accurate that 2 refereed papers came out of that, discovering features astronomers and physicists had never seen before, because we generally don't get to play with the big computers that the visual effects companies do. So because of this final movie version that became iconic, Now even Star Trek gets black holes right. And if Star Trek can do it right, can we do any worse? So digging in a little bit on making a good black hole, of course, we know the physics of how light bends around a black hole is incredibly complicated. It results in bends or even loops, and trying to find a way to do this that maybe is a little more production friendly than the full general relativistic code has been a challenge. But a few years ago, I switched over to using Blender for my 3D work. It's an open source 3D animation visual effects package that has a tremendous community behind it particularly because of its open source nature. And it turns out there are really clever people in that community that already figured out an amazing way to get a good qualitative black hole by basically just creating a series of nested spheres with indices of refraction that were large and decrease as you go out with a little edge blending. And a relatively simple shader tree here, just simple math, the optics tree, you can actually generate pretty amazing, realistic black hole warps. This is an animation some pieces I worked on recently for something that went out for Black Hole Week through JPL on a Black Hole Explainer. And these animations were all done on a single desktop rendering computer using code that I wrote in Blender. I have a kind of quasi simulation running to handle material in the disk. But again, this stuff was basically done on one desktop computer. Even a tidal disruption event, I was able to model using the simulation features in Blender. Again, qualitatively modeled based on actual simulations. So I hope you'll agree that given what we can now just do on our desktops and that people have solved this problem, that a short render black hole is qualitatively in the same ballpark as a full general relativistic ray traced black hole simulation using superconductor clusters. So given that, to the bowling balls and the bathtub drains, at least I personally have come to the statement of never again.
Well, that's my presentation. Are there any questions? I know it's a lot to take in, but in the back?
Yeah, a question. Based on this idea of black holes, I've always kind of pondered, these things going around the universe and they're just kind of grabbing matter here and there, with the idea that they don't ever shrink. Could they also be linked to, I guess, a cycle of the universe, if they never destroy and they always move around and they're gobbling everything up, eventually the two biggest ones on the block are going to come together, right? And that's going to be the only mass left in the universe, right? So in theory, would that eventually become a Big Bang and restart the universe?
Well, there are theories about that, but again, they're unprovable because we don't know what goes on inside of the black hole. So that's one of these theories that I said, I'm not going to touch it with a 10-foot pole because they'll never be able to find evidence for it. And that goes back to my background, not only in theoretical physics, but being an experimental physicist and an observational astronomer. Any others? Yes?
In my old physics lectures, we always taught that once something went into a black hole, that the information of that, whatever went in, is lost. But if black hole evaporates, what happens to that information?
That's another question that's open. And in fact, that was one of the big questions discussed at the Stockholm conference 10 years ago. And the best minds in the planet couldn't come up with an answer for that. Yes?
What's the current thinking about the existence of the supermassive black hole at the center of Sag A?
There's something very dense there, but we don't know what it is. The center of our galaxy is shrouded by a lot of dust. It's dustier than a dust storm out on white sands. All we can get is some infrared and radio observations out of it. It looks like it's the mass, about 3 million black holes is there, but we have no idea what form it takes. All right, thank you. Oh, we'll talk to you.